From Photonics Media, this is All Things Photonics, a podcast where we explore industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, we'll speak with some of the brightest minds in industry and research about the trends shaping the landscape of photonics.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
As longtime readers of Photonics Spectrum magazine know, August is our education issue. Each year, we publish an article covering the recipient of the Teddi C. Laurin Scholarship, given out by SPIE in collaboration with Photonics Media in memory of our company's founder. The scholarship recognizes a student's potential for contributions to optics, photonics, or a related field. Each year, we get to know an extraordinary and promising young mind who has proven themselves to be capable of great things. In that sense, this year is no different. But in another sense, this year's recipient does stand out. For the first time, the scholarship recognizes a high school student. This year's recipient, Jasper Stackawitz, is currently a rising senior at Pennsbury High School in Pennsylvania. It may not be a surprise that he's the president of the school's robotics team, or even that he's dual enrolled at Stanford, but it may come as a surprise that he's leading a nanophotonics project at Stony Brook University. Our interview with Jasper covers his entrance into the world of photonics research, his work with phase change materials, and how the photonics community might be able to reach a younger generation. That conversation is up next. What led you to optics and photonics as a career path?
So I would say kind of the beginning of just my general interest in physics overall was in my freshman year of high school. So when I was a freshman, I took both AP Physics 1 and 2. Specifically, Physics 2 has a chapter in it that covers optics specifically. And I was also a part of our school's robotics club. And kind of those two things in collaboration sort of sparked my interest for physics overall. But in robotics, we were working on this one little project where we were trying to characterize certain underwater objects. So that was anything from fish, to coral reefs and all that stuff. But in doing so, we were using a sort of like light intensity circuit and using a camera and all that stuff. And so I was kind of exposed to real world engineering applications of just optics in general. And so that, in tandem with the theory I was learning, was definitely very interesting. In terms of research itself, my mom is a chemistry PhD, and so she has kind of exposed me to sort of the process of research and where that can bring you as a career path and things like that. And so from there, I kind of decided that I wanted to do more with my interest other than just coursework. And so I began kind of exploring different subfields, different programs and professors that are in the area. And I ended up landing on a professor at Ursinus College named Casey Schwartz. And her research very much stood out to me. It was focusing on photonics specifically. And so I reached out via email and we ended up scheduling a lab tour. So I got to kind of go visit the cool lasers and all the machinery they had there. And that really clicked with me. And then that turned into the research project that I was a part of.
That's awesome. Now, speaking of the research project, I believe this is the one. I understand you've done some work with optical phase change materials.
Yes.
Can you tell us about that work and how it started and how it's kind of developed?
Yeah. So the project that I was a part of was kind of building off some previous work that was done with Ursinus College, like I said, and also University of Central Florida. They have a big school specifically for photonics, actually. And kind of one big area of study has been these phase change materials. Essentially what that is a material where if you switch it between its amorphous kind of cluttered state and a crystalline state, a more rigid, organized state, using any kind of energy transfer that can be electrical or heat or anything like that. These are materials that exhibit big contrasts in their optical properties, some things like refractive index and things like that. And so you have these materials where a small amount of energy is able to completely change how it interacts with light. And so, kind of the work that's been done with that in the past by a variety of people is using these for data storage because they can be treated as a binary system using zeros and ones for the two different states. But their effectiveness for other technologies like integrated circuits and medical diagnostic tools and things like that is kind of limited because the materials that have been studied, specifically things like GST is a common material, which is an alloy of germanium and antimony and tellurium. But it has very poor absorption. It has high absorption loss, meaning that a lot of energy is lost within that transfer. And so we were hoping to kind of study a new material that did not have that problem, which would allow it to be used for more technologies. So we landed on a material called antimony triselenide, which is also known as SB2SE3. And this was a low loss reversible alternative to kind of the phase change materials that were currently being used. We landed on this because of a study that was done almost 60 years ago, where it was used for semiconductors. But more recently, there's been kind of an updated surge in them where, because of their low absorption loss in the kind of visible light region, they have been used as solar cell absorbers for things like solar panels. And so we decided to focus on this material, and we studied this using a technique called drop casting, as opposed to some other methods that have commonly been used. And we kind of examined the properties of this material. We found out it has a very high refractive index contrast, which essentially is just the difference between refractive index in the two different states that I mentioned. We also found the material is very low toxicity, which means that it is safe for consumer application. And overall, just kind of using these techniques, we found out a lot of properties that suggest it could be used for more widespread applications.
Now, I remember in reading Professor Schwartz's letter of recommendation for the scholarship. I believe she mentioned there was some methods for processing glass compositions that you developed. Could you tell us about those?
I could, yes. So I believe that's in reference to, like I mentioned, that drop casting, because when we process that material, it kind of turns into a glass briefly while we're processing it. So essentially, the process there is we first create the alloy of the antimony and selenium, like I mentioned. This is done with very high purity and very controlled setting. So we use 4N pure, which essentially means it's 99.99% pure for both metals. And those are combined into an alloy. And we then placed those in an ampule, and it was vacuum sealed. Um, and in doing so, we were able to ensure that obviously there's no interference from any outside um, things like that. And then we place this ampule in a rocking furnace, which essentially mixes the solution as it's being heated up. We heated it all the way up to 750 degrees Celsius for an entire 12 hours to completely melt and ensure that it was entirely mixed into the uniform ally that we were searching for. And then after that, in order to cool it, we used a technique called quenching, which is essentially just very, very rapid cooling. So we brought the ampule out of the furnace into air of much lower temperature that very quickly solidifies the material and forms a glass-like solid of these two elements, which are now fused. And then from there, we're able to kind of crush it down into a powder and dissolve it in order to drop cast it. But we are left with that kind of glass material after that whole process.
Now, I think you mentioned that this technology has some applications for, or potentially has some applications for, in the medical field.
Yeah.
What sparked your interest in medical applications of photonic technologies. I believe you called that out as a an area of specific interest for you.
Yeah, absolutely. So I would say I'm very exposed via my parents to kind of the intersection of medicine and science. My mother, like I said, has a chemistry PhD, and my dad also has a chemistry degree. And they have both ended up working in more business oriented fields, um, specifically in diagnostics. And so I've been able to see how various technologies are able to enter the medical world just through that lens, and that kind of led me down this path. But looking more into it, there's tons of imaging and diagnostic technologies that utilize lots of photonic materials and technologies. And there's a lot of active research going on in medical physics, which often deals with lots of things related to material science, obviously, in developing all the machines and things like that. And so I'm very interested in obviously real world application, but also being able to help people. I find that being able to see the impact I have on other people is something that's very important to me. And so I think that the opportunity to follow my passion of physics while also being able to help people like that in kind of a medical field would be something very interesting to me. So I've been looking into that definitely.
Now, I guess there's definitely still time to decide, but what do you plan to concentrate on in your college career? There's so many areas of concentration. It's such a diverse field. Is there anything that's kind of really kind of jumping out at you, or?
Yeah, absolutely. Like you said, there's lots of time to explore. I think that my main kind of viewpoint going into college is to keep an open mind and explore and see kind of what things I can find. I'm planning in just being a physics major. I'm potentially interested in a double major in something like data science or computer science to kind of broaden that scope. But I'm definitely interested in more material physics in general. I would like to explore kind of related fields, specifically in the theoretical department. I think that being able to look at it from a more theoretical lens might be something I'm very interested in, just as someone who's uh, well versed in math, or rather very interested in math. I think it would be something interesting to kind of take a step back and look at the theory too, just because it's something I'm not familiar with. But of course, even in optics and photonics, like you said, there's so many different subfields. And so while there isn't anything that's kind of drawing me other than the work I've already done, I think that I definitely want to continue to explore and see kind of what other things are out there through my education.
I guess from your perspective as a student, and somebody who's still in high school, and again, I think you're our first high school student to win this scholarship, which is no small feat. Um, I guess from that perspective and from that viewpoint, what can the optics and photonics community do to garner more interest from students in this field?
Yeah, I think that really the key to it is early exposure. So I think things like demos and outreach events for high school students and even undergraduates is something that has kind of been neglected. I think that, at least in my experience, it sort of felt like there was a high barrier of entry to a field like this. Um, my research mentor, Dr. Schwartz, was very, very helpful, certainly. But before I was able to really even understand what I was going to be working on, I had to read so many papers and look at so much stuff that is just kind of inaccessible to someone who's coming in from the outside without a lot of help. And so I think that, while theory is something that's really interesting to someone that's already in the field and they're able to understand it, it doesn't really do much for someone that has yet to step into that world. And so I think things like active demos, because there are so many really cool things related to optics. I mean, we have lasers and all that stuff. I think there's tons of opportunity to kind of show what problems it can solve, as opposed to kind of letting people come to it through whatever they learn in school or things like that. Just because, I mean, I took a class specifically on optics and it wasn't very application heavy.
Right.
And so I didn't really, I never could have known that any of this was out there just through my coursework. And I also think that kind of promoting the idea that there's interdisciplinary careers available is something that could be very helpful, because there's, like I said, lots of applications like in medicine and in chemistry and even engineering and things like that that come along with photonics because it's so application based. And so I think that if it becomes more obvious to people that may not consider themselves just a physicist that this is something that they can still work in, I think that's something that could have a big impact on kind of bringing people into the field.
Right. I think that's a great point that you make about, sort of I think the theory can certainly scare people off. All the math can be scary
Right.
to students. So I absolutely agree that, show people the lasers, show people the, the cool stuff that you can do.
Exactly.
I think that's a great point.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.